We're back. Yep, we are back. Welcome back. Today, we're just gonna spend an hour or so, maybe 2 hours, preparing for the AP Calc BC review for the upcoming A for anyone who's taking the AP Calc BC this school year. And over the summer, I'm gonna try to try my best to help review for those of you guys uh taking AP Calc BC because look, this course is not for the weak. All right. And yeah, it's gonna be fun. It's gonna be exciting. And I think we can all do good if we actually do good. Yeah, I just solved this. Yeah, but I'll explain it in a minute, right? Using my Microsoft whiteboard. Yeah, let me, I'm sorry guys, I'm gonna have to share the link to a couple of my friends.
Hello.
Guys, I'm gonna have to share the link to a couple of my friends. Couple of servers. No more. So basically, right here, this is the thing, right? What the hell? How do you make this smaller? You know why it's okay. Limit. No, that's my stream. First thing you want to do is, I think you have to multiply by the conjugate. Top in mind. Yep. So the conjugate of what's in the bottom is to get rid of the radical, of course. You just have to do it by the conjugate because that's just a rule. Little algebra 2 review. I think it's very crucial to make sure that your prerequisites, like pre-calc, algebra 2 is like very strong because if they're weak, yeah, you're fried because this course heavily builds on top of that. Make sure to share it with your friends, the link. I'm trying to get 100 views every stream. That's the goal, and I wanna just help other kids who's not good at math be good at math, right? Right. And once you get that, you have to simplify the bottom. The bottom becomes 4 minus x minus 1 if you distribute, because there's actually a negative 1 here, right? And the top is the same. I'm not trying to write everything, so I'll just do that. Make sure it's the top. And look, in order to like simplify this one, just make sure, I mean, just imagine that that then you cross out the factor. Because look, if you know 4 and the 1, they're the common factors. And if you like 4 minus 1 is 3. But then you take out a negative, it becomes uh negative parentheses x minus 3. So that's how I got that in the bottom. And now, okay, so this is the limit as x approaches 3. So now we can plug in 3 for the x because look, you can try doing it first time here, but it's not going to work out because you get 0 over 0, 0, and that's an indeterminate form. Just because it's 0 over 0 doesn't mean that is undefined. It just means you have to do a bit more, a bit more. And yeah, so once you get over here, you have to plug in 3 for the x, and you get 2 plus 3 plus 1, and the square root of 4. Yeah, so the square root of 4, you guys already know is 2, and 2 plus 2 is 4. But is that, so it equals negative 4. And if you see a step-by-step solution, they just did the exact same thing as I did, right? Indeterminate form, 0 over 0. 3, and yeah, just Ooh, this is hard. This one's a bit tricky. Let's watch a video.
Let's see if we can find the limit as theta approaches 0 of 1 minus cosine theta over 2 sine squared theta. And like always, pause the video and see if you can work through this. All right, well, our first temptation is to say, well, this is going to be the same thing as the limit of 1 minus cosine theta as x approaches, or not x, as theta approaches 0, of theta as theta approaches 0, over the limit as theta approaches 0 of 2 sine squared theta. Now, both of these expressions, which could be used to define a function, but they would be continuous if you graph them. They'd be continuous at theta equals 0. So the limit is going to be the same thing as just evaluating them at theta equals 0. So this is going to be equal to 1 minus cosine of 0 over 2 sine squared of 0. Now, cosine of 0 is 1, and then 1 minus 1 is 0. And sine of 0 is 0, and you square it, you still got 0, and you multiply it times 2, you still got 0. So you got 0 over.
I'll be honest, I wasn't that good at pre-calc because for me, pre-calc was like that jump from algebra 2. It's, uh, what can I say? It's not good. Like the jump is real. For those of you guys going from pre-calc to algebra 2, I mean from algebra 2 to pre-calc, it's gonna look bad. It's gonna be pretty bad. Like if you had an A in algebra 2, you might get anywhere as low as a C.
For 0.
That's
So
the
once again,
reality.
we have that indeterminate form. And once it's 0, then you say a different way
It's
is
just
f sine theta,
identities,
the
right?
limit. And big functions
These are
have
just
the signs, the unit
identities.
circled. This
Oh
is a
my
degree,
god.
or b equals 0, f of at theta
This never
equals
goes
0
away. I
expression,
thought it
or a
went
different
away
function
on
definition.
calc, but oh my god. Oh my god. Alright. Wow. So, mm, oh my god. Oh, step one, rewrite tan as sine over cosine. Yeah, identity. Cosine squared theta equals. Yo, guys, I think I need to have a fresh refresh of my trig identities sheet. Yeah, oh my god. I didn't know these would come back. I actually had no idea. Yeah. One, oh, and then you just manipulate it. This is this is a nightmare. This is the good. This is the good stuff. Yeah, I just need to take a quick minute to refresh the brain. Hopefully, uh, this is the good. This is the good stuff. Yeah, I just need to take a quick minute to refresh the brain. So, you need to say step-by-step solution. Oh my God. Yeah, it's complicated and it's hard. Trig identities. Fuck. Hmm. Yeah. This one, this one, yeah, this one you just have to really think about. Yeah, I'll try my best to explain it from the answer key. If you like substitute x equals pi over 2, you get 0 over 0. And uh, right. And you just have to rewrite some stuff to make things easier. So cotangent, okay, we have to rewrite this. Cotangent squared x to cosine squared over sine squared x. Okay, okay. I don't think, never knew limits were this hard. Damn, damn. Cotangent x cosine over sine. Damn. Oh, don't understand. plus 1 minus sine 1 plus cosine. Yeah, and then you just have to cancel the like terms, and you get uh, sine of pi over 2 is 1. No, 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 no. Sine pi over 2 is 1. 1 plus 1 equals 2. And then sine squared x. What? So in the bottom is, I'm assuming it equals 1 sine squared pi over 2. Sine, is 1. Yeah. How? It makes 0 sense. I'm assuming sine pi over 2 is 1, and then if you square it, it's also 1. So you get 2 over 1. And that's just the way it is. That's just the way it is. Oh my god. Another one. Theta approach is pi over 4. I'll try to do this by myself because I already had 2 examples. Yeah, I need some help. Chat. Chat. Chat, I need help.
We're back. Yep, we are back. Welcome back. Today, we're just gonna spend an hour or so, maybe 2 hours, preparing for the AP Calc BC.
When I'm not with you.
review for the upcoming for anyone who's taking the Pre-Calc BC this school year. And over the summer, I'm gonna try to try my best to help review for those of you guys taking Pre-Calc BC, because look, this course is not for the weak. All right, and yeah, it's gonna be fun. It's gonna be exciting, and I think we can all do good if we actually do good.
Yo,
Yeah, I just
I'm
solved
actually about
this.
to crash out.
Yeah, man, I'll
Oh
explain
my god.
in a minute, right? Using my Microsoft whiteboard.
So confused. This is, I'll admit, this is my weakness. Oh my goodness. I'm gonna skip that
Multiple
back to
videos and
square one.
exercises, we cover the various techniques for finding limits. But sometimes it's helpful to think about strategies for determining which technique to use. And that's what we're going to cover in this video. What you see here is a flowchart developed by the team at Khan Academy, and I'm essentially going to work through that flowchart. It looks a little bit complicated at first, but hopefully it'll make sense as we talk it through. So the goal is, hey, we want to find the limit of f of x as x approaches a. So what this is telling us to do is, well, the first thing, just try to substitute what happens when x equals a. Let's evaluate f of a. And this flowchart says, well, if f of a is equal to a real number, it's saying we're done. But then there's this little caveat here, probably. And the reason why is that the limit is a different thing than the value of the function. Sometimes they happen to be the same. In fact, that's the definition of a continuous function, which we talk about in previous videos, but sometimes they aren't the same. This will not necessarily be true if you're dealing with some function that has a point discontinuity like that, or a jump discontinuity, or a function that looks like this. This would not necessarily be the case. But if at that point you're trying to find the limit towards, if as you approach this point right over here, the function is continuous, it's behaving somewhat normally, then this is a good thing to keep in mind. You could just say, hey, can I just evaluate the function at that a over there? So in general, if you're dealing with pretty plain vanilla functions like an x squared, or if you're dealing with rational expressions like this, or trigonometric expressions, and if you're able to just evaluate the function and it gives you a real number, you are probably done. If you're dealing with some type of a function that has all sorts of special cases and it's piecewise defined, as we've seen in previous other videos, I would be a little bit more skeptical. Or if you know visually around that point there's some type of jump or some type of discontinuity, you've got to be a little bit more careful. But in general, this is a pretty good rule of thumb. If you're dealing with plain vanilla functions that are continuous, if you evaluate at x equals a and you get a real number, that's probably going to be the limit. But now let's think about the other scenarios. What happens if you evaluate it and you get some number divided by 0? Well, in that case, you are probably dealing with a vertical asymptote. And what do we mean by vertical asymptote? Well, look at this example right over here, where you're just saying the limit, then a darker color. So if we're talking about the limit as x approaches 1 of 1 over x minus 1. If you just try to evaluate this expression at x equals 1, you would get 1 over 1 minus 1, which is equal to 1 over 0, which says, okay, I'm falling into this vertical asymptote case. And at that point, if you wanted to just understand what was going on there, or even verify that it's a vertical asymptote, well, then you could try out some numbers, you could try to plot it, you could say, all right, I probably have a vertical asymptote here at x equals 1. So that's my vertical asymptote. And you could try out some values. Well, let's see, if x is greater than 1, the denominator is going to be positive. And so my graph, and you would get this from trying out a bunch of values, might look something like this. And then for values less than -1, or less than 1, I should say, you're going to get negative values. And so your graph might look like something like that. And so you have this vertical asymptote. That's probably what you have. Now, there are cases, very special cases, where you won't necessarily have the vertical asymptote. One example of that would be something like 1 over x minus x. This one here is actually undefined for any x you give it. So it would be you will not have a vertical asymptote. But this is a very special case. Most times you do have a vertical asymptote there. But let's say we don't fall into either of those situations. What if when we evaluate the function, we get 0 over 0? And here is an example of that. Limit as x approaches -1 of this rational expression. And let's try to evaluate it. You get -1 squared, which is 1, minus -1, which is plus 1, minus 2, so you get 0 in the numerator. And then in the denominator, you have -1 squared, which is 1, minus 2 times -1, so plus 2, minus 3, which is equal to 0. Now, this is known as indeterminate form. And so on our flowchart, we then continue to the right side of it. And so here's a bunch of techniques for trying to tackle something in indeterminate form. And likely in a few weeks, you'll learn another technique that involves a little bit more calculus called L'Hopital's rule that we don't tackle here because that involves calculus, while all of these techniques can be done with things before calculus, some algebraic techniques and some trigonometric techniques. So the first thing that you might want to try to do, especially if you're dealing with a rational expression like this and you're getting indeterminate form, is try to factor it. Try to see if you can simplify this expression. And this expression here, you can factor it. This is the same thing as x, x minus 2 times x plus 1 over, this would be x minus 3 times x plus 1. If what I just did seems completely foreign to you, I encourage you to watch the videos on factoring polynomials or factoring quadratics. And so you can see here, all right, look, if I make I can simplify this because as long as x does not equal -1, these two things are going to cancel out. So I can say that this is going to be equal to x minus 2 over x minus 3 for x does not equal -1. Sometimes people forget to do this part. This is if you're really being mathematically precise. This entire expression is the same as this one because this entire expression is still not defined at x equals -1, although you can substitute x equals -1 here and now get a value. So if you substitute x equals -1 here, even if we're formally taking it away to be mathematically equivalent, this would be -1 minus 2, which would be -3, over -1 minus 3, which would be -4, which is equal to 3/4. So if this condition wasn't here, you could just evaluate it straight up, and this is a pretty plain vanilla function. I wouldn't expect to see anything crazy happening here, and if I can just evaluate it at x equals -1, I feel pretty good. So once again, we're now going factoring. We're able to factor. We simplify it. We evaluate the expression, the simplified expression now, and now we were able to get a value. We were able to get 3/4, and so we can feel pretty good that the limit here in this situation is 3/4. Now I would categorize what we've seen so far as the bulk of the limit exercises that you will likely encounter. Now the next two, I would call slightly fancier techniques. So if you get indeterminate form, especially you'll sometimes see it with radical expressions like this, rational radical expressions, you might want to multiply by a conjugate. So for example, in this situation right here, if you just tried to evaluate it x equals 4, you get the square root of 4 minus 2 over 4 minus 4, which is 0 over 0. So it's that indeterminate form. And the technique here, because we're seeing this radical and a rational expression, is hey, maybe we can somehow get rid of that radical or simplify it somehow. So let me rewrite it. Square root of x minus 2 over x minus 4. When we say conjugate, let's multiply it by the square root of x plus 2 over.
Right, direct substitution. Try to evaluate the function directly. So let me try explaining this because maybe that's the only thing I can do. Just explaining the answers instead of finding the answer. So strategy and finding limits. You want to calculate the limit as x approaches a of f of x. The first step you do is you do the direct substitution. And when you do direct substitution, you get three outcomes. You get a number over 0, which probably means that there's an asymptote of some sort. Right, and then the example is when a limit as x approaches 1, 1 over x minus 1, you get 1 over 0. Now, the second option is you get f of a is a real number. So when you actually do direct substitution, you actually get a real number. So the example we see is when a limit as x approaches 3, x squared, if you plug in direct substitution, 3 to x, you get 3 squared, and that equals 9. And that's just the answer. But normally, it's just not going to be that simple because, yeah, it's just not. More often than likely, we get, when we plug it in, you get 0 over 0. And you have to do a lot more, right? Sometimes, when you get that, you might have to factor x squared minus x minus 2 over x squared minus 2x minus 3. Now, in that situation, you will learn it in a later unit called the L'Hospital's rule, where you just take the derivative of top and bottom, but we're not into derivatives yet. We'll get into that later, but yeah, just factor it out. X minus 2. What? No, it's I think it's like, I don't know, you factor it. X minus 2 and x plus 1, x minus 3, and x plus 1. And you cross out the x plus 1s, and you get x minus 2 over x minus 3. And you get an answer. And conjugates, they're harder than factoring, of course, but it's not impossible to understand. So, oh, you get that, for example, multiply top and bottom by the reciprocal, and you cancel the familiar conjugates. I mean the familiar factors, and you cancel, and then you get a new thingy. And trig identities is the hard one. You have to just know that sine squared plus cosine squared equals 1. Sine over cosine is tangent. And you just have to manipulate it, you know? Use the basic trig identity. And you have to manipulate it, use it around. It's tricky. It's tricky, it's tricky. But it's not too hard. I don't think it is. It's not too hard. An approximation, when everything fails, graphs and tables can help approximate. Yeah. Practice with direct substitution. We want to find the result is indeterminate. Dude, if it's this, is you usually get indeterminate. 4 minus 3 is 1. 1 over 9, 3. Oh, it's B. It's 1 over something, yeah. What happens when we use direct substitution as x approaches 0? Cosine of 0 is cosine of 0 is 1. So you get 1 minus 1 is 0, and sine squared 0 is 1. and 2 times 1 is 2. And so 0 over 2? No, I did something wrong. I think it's indeterminate. Yeah, 0 is 0. Justin tried to find the limit as x approaches -1. Oh. When x plus 1 over x squared plus 3x plus 2. What? Wait, what? Tangent tangent pi is 0, and then 0 cosine of pi is -1? What? Yeah. Trig identities. Rationalization. No, wait. Yeah. Vector and trig. What? How do you do this? Wait, what? That doesn't make sense. No, I don't know what to put. That doesn't make sense. Mm. Oh, you do it like that? This shit retarded. Oh,